Alrighty, we're going to put a couple of more tools in our toolbox today in our study of kinematics. We're going to add the definitions of speed and velocity. Now, I think speed is probably something that everybody's pretty familiar with. You drive down the road and you're familiar with speed limits, especially if you're already driving. Your parents may have specifically warned you don't speed. If you get caught, the speeding ticket's your responsibility. I'm not paying for that for you. So speed and velocity, however, are very, very different things because we were talking about scalar and vector quantities before, and we were talking about distance and displacement. Well, speed talks about how much distance you cover in a certain amount of time. Now, time is also a scalar quantity because as far as we know, it only goes one direction. And so there's not going to be any direction to it because it only goes one direction. Remember, scalar does not have a direction to it and a vector quantity does. So speed is actually when I take the distance that's been traveled and I divide it by the amount of time it took to go that amount of distance. So that will give me speed. Displacement, when I take that and divide it by time, that gives me velocity. So if I'm going to add these two things to my chart over here, speed will go on the scalar side and vector will go on the velocity side. And it's a neat way to remember that is that scalar and speed both start with S and vector and velocity both start with V. So we've got a couple of problems where we're practicing what the difference is between speed and velocity. So again, speed requires distance, velocity requires displacement. So if you look at example 1.2, they're talking about a bicycle trip where you start at your house and you ride 15.1 meters in one direction in 25.2 seconds. And then when you get to the end, you turn around and you ride 15.1 meters back and you take the return trip in 27.1 seconds. So in this problem, they've asked you to find both speed and velocity. Well, the formula for speed is equal to the change in distance over the change in time. And that triangle is a Greek letter delta, which stands for the change in. And so once I get formulas for speed and velocity, these are formulas that you're going to want to put on your little card so that you can have those as you're working all the way through the chapter and then when you get down to the test at the end. So these two would be the first formulas that are going to go on there. So for this particular one, I'm looking at distance. So with distance, I'm not looking at positive and negative numbers at all. So here, my distance is going to be 15.1 meters down and 15.1 meters back. And then on the bottom, it took me 25.2 seconds down and it took me 27.1 seconds to go back. So what that gives me then is 30.2 meters total that the bicycle has traveled and 52.3 seconds as far as the total time that's been traveled. So when you divide that out, you end up with 5.78 meters per second. Now, I want to just make a quick note on significant figures. All of these were taken out to the tenths place, so when I added them, I left them to the tenths place. But when I divide, I've got 3 significant figures on the top, and I have 3 significant figures on the bottom, and so my final answer should also have 3 significant figures. So what does this mean, meters per second? Well, that means every second you traveled 5.78 meters. So you traveled 5.78 meters in the first second, 5.78 meters in the second, 5.78 meters in the third second. So the amount of distance you're traveling per second is the same. Now let's look at velocity because velocity is the displacement. So when I look at the displacement, that's usually defined as, in place of a D, they usually use an X for that with a delta T on the bottom. So delta x, now is where I have to use my positive and negative numbers. So I went 15.1 meters down, and then I want a negative 15.1 meters back, because that's how I'm going to get displacement over the 52.3 seconds that I had before. Well, what's that give me? 15.1 plus negative 15.1 is 0, so I'm going to have 0 over 52.3, which is a 0 meters per second. Wait a minute. How can that be? How can speed be one thing and velocity be something else? Well, this is where the definitions come in, because velocity means displacement. You ended up in exactly the same place where you started. And because you had no displacement, therefore you had no velocity. You definitely had speed, but you don't have any velocity because you ended up in the very same place where you started from. Okay, so that's the difference between the two. So now let's look at the second part of example 1.2. We're talking about a sprinter in this, and it talks about how the sprinter is running a 200-meter dash, and he runs it in 24.00 seconds. Then he turns around and he walks back to talk to his coach, who evidently is standing up here, and he's so tired that it takes him 25 seconds to walk this 15 meters back. And the problem is asking for velocity in each stage of his trip here. So when I drew my diagram, I made sure that since I'm asked for velocity, I made the direction towards the finish line positive and the direction back from the finish line negative. Again, that's arbitrary. You could have done it the other way around. It doesn't make any difference as long as you remember which way is which, and as long as you put that in your answer. You'll notice I didn't put any direction up in this problem just simply because there wasn't any velocity, so there was really no point in putting a direction there either. So if I want the velocity for the first part of the trip, velocity is going to be delta x over delta t. So I'm going to have 2.00 times 10 to the second meters over 24.00 seconds. Now why didn't I just write 200 meters? Well, again, because I'm looking for three significant figures. And so when I take that and divide it out, I'm going to get 8.33 meters per second toward the finish line. Okay? Positive number, so that means it's towards the finish line in one direction. There are three significant figures in the answer because I have 3 here and I have 4 here, so I'm going to use the smallest number of significant figures when I multiply and divide. The second part of the problem asks for his velocity when he goes back to talk to his coach. So for that portion, delta x over delta t, I'm going to have a negative 15 meters over 25 seconds. Okay, remember velocity has everything to do with direction, so that's why this number needs to be negative. So when I divide that, I'm going to end up with a negative 0.60 meters per second away from the finish line. And you're going, wait a minute, a negative velocity? How can you have a negative velocity? Velocity is not the same as speed. Velocity has to do with the direction that the object is going. So yes, it is negative because he is coming back this way. Okay, so it's negative because it indicates the direction that he's going. Then finally, it's asking me for the velocity over his entire trip. So when I do that, I'm going to have 2.00 times 10 to the second meters plus a negative 15 meters over 24 seconds for the first half of the trip plus 25 seconds for the last half of the trip. Okay, now we have to be careful with significant figures when we're adding and subtracting here. Here I have the ones place or the units place, depending on the math program you use, that's going to depend what that particular digit is called. This is the significant figure that I've got to carry the rest of my numbers to. So therefore, that means that I'm going to have 185 meters on the top. If you notice down here, this first time was taken out to the hundredths place, but this was only taken to the units or the ones place. And so my answer when I add is only going to be able to go to the units or the ones place as well. So when I add 24 plus 25, I'm going to get 49 seconds, but I'm not going to have anything after the decimal point. Now when I divide, I've got 3 significant figures divided by 2, so I'll have 2 significant figures in my answer. So that will be 3.8 meters per second. And this did come out to be a positive number, so it's 3.8 meters per second toward the finish line. Now, one thing I want to point out here, and that's that you cannot take this velocity and average them together to get the velocity for the whole trip. This one's pretty easy to see why it doesn't work, and the reason is because here you would be adding, you have a positive velocity and a negative velocity. They're for very different amounts of time, and so because they're not for the same amount of time, you can't simply add the 2 velocities together and divide it by 2. That won't work. Okay, so when you're asked for velocity for the entire trip, you have to make sure that you get the total displacement for the whole trip over the total time for the whole trip. Don't try to take a shortcut and just take those 2 numbers and average them together, because as I said, it's not going to work. And if you tried that, you're certainly going to see that it's not going to come up anywhere close to 3.8. All right. Finally, in example 1.3, the thing I want to make sure that you notice there is that you really have to watch units when you're working some of these problems. Let's make some more space up here again. That's one thing that the author of this textbook kind of seems to enjoy doing, is you're chugging along doing all sorts of problems, and then all of a sudden he throws one in where the units on the numbers that he's given you do not match. And so you have to be really careful about that so that you don't end up getting thrown off. So example 1.3 talks about a jogger running down a long straight country road at 2.3 meters per second. If she jogs in that direction for 15.3 minutes, how far does she run? Okay, so the jogger's going one direction here, but the problem is my velocity is in meters per second, 2.3 meters per second, but the time that they've given me is in minutes. And if I try to just plug that into my velocity formula, seconds and minutes are not going to cancel out with each other, so you have to make sure you convert. This conversion should be relatively simple. Remember that when you do conversions like this, you always take what they give you and you put it over 1, and then you're going to arrange your conversion factor so that you cancel out the part that you do not want and you get the part that you do want. So since I want seconds, I know that seconds has to go on the top. I'm trying to get rid of minutes. Minutes has to go on the bottom. In 1 minute, there are 60 seconds, so minutes cancels out. And then when I take 15.3 times 60, that's going to give me 918 seconds. Now, you may be looking at that going, Mrs. Thompson, you didn't obey significant figures. Actually, I did. This has 3 and this has 3. There are exactly 60 seconds in 1 minute. And so you could think of this as being 60.00000 and 1.0000 and an infinite number of zeros afterwards. So conversion factors in the majority of the time are not used in significant figures. There are some exceptions to that. I'll let you know when we come across one that you do have to remember those significant figures in the conversion factor, but for something like this, you don't worry about significant figures from a conversion factor. So I had 3 here, so I've got 3 here. Now, because I know a velocity and a time, I can then use algebra to calculate my displacement. So if velocity equals delta x over delta t, the velocity is 2.3 meters per second. The displacement's what I'm trying to find, and the time is 918 seconds. So if I multiply both sides by 918 seconds, I'll end up with my displacement. And my displacement is going to be 2,100 meters for delta x. 3 significant figures here, 2 here, so I need to have 2 in my answer. And since it is displacement, I also need to give a direction. Really, the only direction they gave me in the problem is that she's going down the road, so it would be 2,100 meters down the road. Okay, so speed and velocity, speed being scalar, vector, or velocity being vector, so you want to make sure that you're watching significant figures. You want to make sure that you're always including a direction with the final answer in your velocity.